Hi, my name is Vaibhav Vavilala. I'm a PhD student at the University of Illinois at Urbana-Champaign, and I'm excited to share with you my work in convex decomposition of indoor scenes. Parsing complex objects into simple geometric primitives has been an exciting area in computer vision for many years. Previous work has decomposed ShapeNet objects into coarse abstractions, in some cases with semantic meaning, like separating the seat, legs, and a backrest into independent cuboids. Geometric compression and physical simulation could be other applications for primitive decomposition. In this work, we want to predict simple geometric primitives from a complex, cluttered indoor scene. A simple geometric abstraction can allow us to reason about the high-level layout of the scene and simplify unnecessary details. We made 4 contributions. First, we standardized evaluation of primitive decomposition methods, benchmarking to existing depth, normal, and segmentation error metrics. Second, we improved the quality of primitive decomposition as measured by fidelity to the original depth map. Third, our hybrid method is unique in that we first use a learned regression-based procedure to predict a start point, and then polish the primitives via descent at test time per image. Finally, we use segmentation to drive primitive generation. Our method accepts an RGB image, a depth map, and a segmentation map. An RGBD image is the input to a CNN encoder-decoder, which predicts the best primitive representation for this image. During training, a series of losses are applied to the sample points and primitive representation to update the network weights. At inference, we directly optimize the primitives with respect to the losses to improve the fit. The depth and segmentation can be inferred by an off-the-shelf pre-trained network if ground truth isn't available. Our method starts from the CVXNet architecture and losses, but for this work, we use the NYU V2 dataset. To create samples from a depth map, we rely on a simple heuristic to generate free space and surface samples, where each sample is labeled as inside or outside. Additionally, we introduce 2 losses. First, a Manhattan world loss encourages the primitives to approximately follow a Manhattan world and improves the overall organization of parts. Second, our novel segmentation loss encourages each primitive to have only one label and improves behavior on some scenes. In these results, the top row shows the input RGB image, the second row shows the most recent prior work, and the bottom row shows our method, which generally does a better job covering the space with primitives. On the left, our table shows that our method creates primitives that generally respect the depth map more closely than prior work. On the right, we show that our method does a better job getting finer details right in the primitive decomposition, like the pillow on the bed. In this ablation, we show that our method still works well even when ground truth, segmentation, and depth are not available at test time. Our network never sees the right answer. Instead, it predicts the solution to an optimization problem via regression. We find that regress, then polish, is much better than either regress only or polish from a random start point. Here we demonstrate that our Manhattan world losses improve the overall look of our generated primitives, as well as the error metrics. We report a number of natural variants, including splitting our primitives at inference. Extensions to our work include analyzing the latent space of our encoder, investigating other primitive representations, and generating multi-view consistent primitives. Thank you.